Good morning, David. We have 2 more minutes.
Morning.
Would you like to show your video?
Yeah, I'm just getting it set up.
Hello. Well, 1 more minute. How is the course going for you?
Yeah, I'm finding it okay. There's some stuff that's like familiar from undergrad and some stuff that's new, but
okay, good. You have an undergraduate electromagnetics course.
Yeah.
So where did you take your course?
The University of Queensland in Australia.
Oh, Australia, Queensland.
Yeah.
Okay, very good university.
Yeah, I did a few electromagnetics actually. So like, because I did some optics and some microwave specific courses as well. So some of the transmission line stuff for microwaves is very familiar. Some of the optics, like the cavity stuff is a little bit familiar, but.
Mm-hmm. Okay, good. Queensland actually has a good group of quantum technology. Australia is doing very well in quantum technology. So
yeah, I don't know so much about the quantum, but I did an undergraduate thesis with a guy who did optics stuff with Bell Labs in New Jersey. So
were you with the ECE department at Queensland?
It was ITEE. ITEE.
ICEE. What does that stand for?
IT.
Or ITE.
In electrical engineering.
Okay.
Yeah, there's some good stuff going on there research-wise. It's quite interesting.
Okay.
They have quite a good microwave research group as well.
Yeah, it should be. Yeah. So I guess I see that it's 10:30. We can get started, I suppose. We see Jason Johnson here. Hi, Jason. Good morning. Okay, do we have any questions before we get started? Well, if not, let me share my screen. And can you see my screen? Well, today I'm going to talk about Holo waveguides. It is actually quite an interesting topic. We will just show you how it works, and then the great thing about Holo waveguide is that it provides closed form solutions to a few problems. So because Holo waveguides have closed form solutions, the closed form solutions can offer physical insight. Okay, so what happens is that we have studied a couple of waveguides before already. We have studied transmission line, which is actually a kind of waveguide. Okay, we have transmission line. Then, as you can see in your homework, it is a waveguide because you can write it symbolically as such, but when you actually make this waveguide, you might want to make it out of a coaxial cable, for instance. And then if you look at the electromagnetic field inside, you have electric field that looks like this. And then you have magnetic fields that looks like this. Okay, so this is the E field, this is the H field. And we show in your homework that is due today that you can actually find this electric field and magnetic field, and then find the telegrapher's equations, which is that dV dz is minus j omega Li, the I dz is minus j omega CV, Okay, and those are the telegraphist equations, and they can also be derived using Maxwell's equations. And then we went and studied transmission, let me call this transmission line. Okay, then we study next the dielectric waveguide. Dielectric waveguide is just formed from the fact that you have one area which is optically more dense than the surrounding area. Then total internal reflections can occur at the boundaries, and the wave can be bouncing back and forth between the two boundaries and get guided. The noted very important feature is that because of total internal reflections, the wave outside the waveguide is evanescent. Okay, that is something that you should be conscious about. Okay, and then from dielectric waveguide theory, you can also get the thin film waveguide, where you have metal on one side, optical thin film waveguide. You just coat a piece of metal or a metal surface with a dielectric layer like glass or something like that, and then you can use that as a waveguide. Or you can also make what we call a parallel plate waveguide, where you put two parallel plates. This would be PEC, such that the conductivity goes to infinity. The electromagnetic signal cannot penetrate the metal region, and then the wave will have to bounce back and forth. So the guidance is mainly by bouncing back and forth between the two boundaries in many waveguides. And in the case of a coaxial cable, the guidance is more or less by having a resonant circuit, so that you can see that there is a exchange of energy between the LC circuits that you can have in the transmission line, because you can approximate the transmission line with a series of inductors and capacitors. And as the wave propagates, there will be inductance energy stored, and then there will be capacitance energy stored. The energy just gets swapped back and forth between those in the capacitance and those in the inductance, and then the wave can propagate along. Okay, so today we're going to study hollow waveguides, and hollow waveguides have the advantage that you can have quite a bit of closed form solutions. Okay, so you have a hollow waveguide. Schematically, it looks something like this, but then examples of hollow waveguides are rectangular waveguides. Okay, you have maybe a pipe. Essentially, you call people who make waveguides plumber. This is quite popular in microwave engineering. Okay. And the hollow waveguide can trap a wave, and let me draw it to be correct schematically. So a rectangular waveguide can make a hollow waveguide, or you can have a hollow pipe, which is circular. Okay. And those can make waveguides. But there's a peculiarity about hollow waveguide, which is that it cannot support a TEM mode. Okay, no TEM mode. The TEM mode is characterized by the fact that the electric field and the magnetic field, both of them are transverse to the direction of propagation. An example of a TEM wave is a plane wave. If this is your K vector, and this is your E field, and this is your H field. Let me see if I draw it correctly. This should be my E field. This should be my H field. And this should be 90 degrees. Okay. And three of them together make the right-handed coordinate system, with the fact that E cross H points in the k direction. This has to be true. This has to be true from Poynting's theorem, because you know that from Poynting's theorem, E cross H is the direction of energy flow, and hence it has to point in the k direction. So this is a TEM wave. And you can have that when both the electric field and the magnetic field are orthogonal to the k vector, the direction of propagation. And we like to prove that no TEM mode inside the waveguide, which means that if this mode exists, EZ equal to 0, HZ equal to 0, Z being the axis, okay, Z being the axis of the waveguide. So there are no waves where both EZ and HZ are 0. And we can actually come up with an argument that proves that this is so by the proof of contradiction. Proof of contradiction, okay? Let me see, I have to get rid of this. Okay, how do we prove by contradiction? And so in Latin, this is called reductio ad absurdum. This is a little bit of Latin that I know from the scientific literature, Latin word for proof by contradiction. What you can do is to first assume that the TEM wave exists. And you can actually prove that if a TEM wave exists, then the magnetic field would have to look something like this in the picture over here. Okay, the magnetic field will have to look something like this. It has to look something like this because a metallic waveguide does not have magnetic charges. Because it does not have magnetic charges, there's no way for the field to end on the waveguide wall. Okay, so the electromagnetic field, especially the magnetic field part, has to form a closed loop in this manner. And because it's a TEM wave, the electric field is purely transverse to the direction of propagation. Okay, so if this does exist, then we have a contradiction, because if the magnetic field is there, then if we perform this integral on Maxwell's equations, and this integral on the Maxwell's equation says that it has to be, by Ampere's law, equal to d dot ds on the right-hand side, and then must be equal to the current, ds on the right-hand side, okay? Where the S is this region that is enclosed by C, okay? And you can clearly see that if H looks something like this, it is always pointing in the same direction as your DL. And if you pick a DL to be along this circle, the left-hand side is not equal to 0. The left-hand side is not equal to 0 for sure for this picture that we have drawn. But then the right-hand side, if there's no metal pieces, there's no current in it, then this has to be 0. But then if the field is TEM, then this is also equal to 0 if DZ equal to 0. Okay, I'm going to take my S, and my DS would be something that has a component that is normal to this surface S. So DS is pointing in the Z direction, and if DZ is equal to 0, this dot product is 0. Okay, so both the terms on the right-hand side are 0, but the left-hand side is not equal to 0. So this is not possible. So a case where you have a TEM mode, where the left-hand side gives rise to non-zero value, but the right-hand side equals to 0 is a contradiction, and hence this mode cannot exist. Are there any questions on the proof of the absence of a TEM mode by contradiction? However, you can remove this contradiction by, well, if I have a waveguide, if I have a metal piece in the center, and then this metal piece can carry J. If J is not equal to 0, then you wouldn't have a contradiction because the magnetic field goes around like this, the H field. And the left-hand side is not equal to 0, but then you can have a current flow. And the current flow would make this term not equal to 0. And there's no contradiction to have both left-hand side and right-hand side not equal to 0. And you can still have the Z equal to 0 then. So you can still have EZ equal to 0, HZ equal to 0. And this is the case of a coax. And in the case of a coaxial cable, you see that the magnetic field is something like this. Okay, there's H field, and if you look at the E field in your homework, the E field looks something like this. Okay, in the coax cable, you can have a TEM mode, and it can exist. Okay, so any questions on this? If not, then let's move on to a hollow waveguide and take a hollow waveguide more seriously. So we can, in general, solve for the solution of a mode in a hollow waveguide in closed form, and then we can say that a hollow waveguide looks something like this. Say, let me see, do I have a picture of it? This is one picture, and this is another picture, which is a typical hollow waveguide. So let's assume that it will be, in general, something like this, a hollow piece of metal. Then we look for solutions inside this waveguide, and we will first study the TE case. Okay, I actually put the picture in the wrong place. We study the TE case, and in the TE case, it implies that the electric field is transverse to the direction of propagation on Z-axis, so EZ must be equal to 0. But you can also show that since both of them cannot be 0 simultaneously, HZ has to be non-zeros, so that this is not a TEM wave, this is a TE wave. Okay. Then we want to construct a solution inside the waveguide. We will use the pilot vector approach. In this approach, you define a pilot vector. The pilot vector is something that points in the Z direction. Okay, let me use a subscript H to represent this pilot vector. And then if I take the curl of this pilot vector, or pilot vector function, then the electric field is equal to that. And by construction, you can see that since it's something that is formed from the cross product of del with a Z, and it definitely have EZ equal to 0. Okay. Furthermore, because it is a curl of something, and what do you think the divergence of E should be for this field that we have constructed this way? We have chosen to construct an E field using the pilot vector and the pilot potential. What do you think the divergence of E should be?
Shouldn't it be 0?
What?
The divergence of E, shouldn't it be 0?
Yes, it should be 0. Very good. Who was that speaking?
It's Nanian.
It is who?
It's Nanian.
Yeah, your speaker is very noisy. I don't know why. Okay, your speaker is very noisy. Maybe you're outdoor. I don't know the reason. but the divergence of E equal to 0. And by that, when the divergence of E equals 0, what does it mean to you physically? Does anybody want to offer an answer as to what the physical meaning of divergence E equal to 0 means? If
There's
it's
no
not,
enclosed charges.
it is what?
There's no enclosed charges by
There's no
Gauss's law.
charges inside the waveguide. It's source free. Okay. Source free. Otherwise, divergence of E is equal to charge. Normally, if divergence of E is not equal to 0, if there are sources inside the waveguide, that should be equal to the charge in the system. But since we're dealing with the hollow waveguide, which is source free, then that should be the case. Okay. Then we have to ensure that Maxwell's equations is satisfied. So what we do then is to make sure that the curl of E, which is Faraday's law, should be equal to J omega mu H. Okay. And then we also can take a double curl on the left-hand side. And we assume that mu is a constant. Mu is constant independent of space. Then we have this curl of H on the right-hand side. And we can infer what curl of H should be from Ampere's law. Okay, Ampere's law says curl of H is equal to J omega epsilon E plus J. But J equal to 0 because we are in the source-free region inside the waveguide. And then if you plug this in now, this should be omega square mu epsilon E on the right-hand side. And what is double curl equal to? Double curl on the left-hand side. Anybody? I think by the time of this course, at this juncture, you should have this knowledge like the back of your hands. Okay, curl of E equals anybody? If you use the back of the cat formula in your head, or you can.
Shouldn't it be omega square mu epsilon?
What is that again?
The thing that we use for Helmholtz equation, like omega square mu epsilon E.
Oh, you're repeating the equation on top for me. I want to simplify the left-hand side using some vector identity that I have learned. So what would the left-hand side be equal to? Anybody?
Grad of the divergence of E minus the Laplacian of E.
Very good. Okay, this would be equal to the gradient of the divergence of E minus this thing, which this is equal to 0 because we are in a source-free region. So this would be equal to Laplacian of E. So this del dot diff dot del, which is usually called the Laplacian, can be written in abbreviated notation as such. Then what you have is that the E field, if you put everything together now, you have the E field must satisfy this equation. Okay, the E field must satisfy this equation. I take this to the left-hand side becomes this, and this is just Helmholtz equation. Okay, this is just Helmholtz equation. And now we need to prove that this is a solution to Helmholtz equation, if this is going to be something reasonable. So what does it take to make this to be a solution to the Helmholtz equation? Let's see if I can insert a new slide. Okay, it turns out to be blank. Sometimes it's blank, sometimes it's not. So let's try to plug this in here, this term inside here, and try to observe what it takes for phi sub h to be in order for this equation to be satisfied. So let's look at this this thing first, which is that when we plug that in, then you will get Laplacian plus beta square. Let me call this thing beta square. Okay, this is just beta square. And then when you plug that E representation in, you have just, and this has to be 0. And I'm going to use a mathematical knowledge that all of us should know, which is that if you have a Laplacian operating on the curl of Z size of H, this should be equal to the same of curl of Z Laplacian of size of H. Okay, you can show this by direct manipulation. You can plug in all the gory details of what the curl of Z hat is. This is a scalar operator, and if you go through every term, you can show that the curl, the Laplacian can be put to the right-hand side of this operator. And of course, you can now rewrite the top equation and write it as curl of Z hat Laplacian plus beta square size of H equal to 0. Okay. And one way to have this equation satisfied is to require that my size of H satisfy this equation. Okay, if my size of H satisfies this equation, it implies that this equation would be satisfied. Let me just put the beta square here. Okay, if you work this backward, this is the solution of this equation that you want to look for. Okay, this is the solution of this equation that you want to look for. And you can work backward, that when this equation is satisfied, it implies that this equation is satisfied. And it also implies that this equation is satisfied. And whatever you have inside the waveguide satisfies Maxwell's equations. Okay. So this concept is known as the commutation. The fact that you have two operators, the commutation between two operators, like matrix operator, for instance, is defined to be A dot B minus B dot A. And if this is equal to 0, if A dot B equals to B dot A. And when this happens, you say that the two operators commute. That means that you can exchange the order of operations and they're still equal to each other. And we have shown that these two operators in fact commute. This is called a commutator in mathematics. Okay, so we have arrived at the equations that should be satisfied by phase of H. And in order to solve this problem, it is a partial differential equation. It cannot be solved unless we also figure out what the boundary condition should be. So the next task is actually find boundary condition. Okay, find the boundary conditions. If this is a metallic waveguide, what do you think should the boundary condition be on the waveguide wall? Anybody wants to volunteer an answer? If you have a metallic waveguide, let's assume that the metallic waveguide is made of perfect electric conductor. What should the boundary condition be on the waveguide wall? Anybody? So what should that boundary condition be on the waveguide wall?
Professor,
Yes.
For the electric field, the normal vector of the electric field should be 0 along any contour.
I think you remember things wrong. We talked about boundary condition at a metal surface or a metallic surface. Okay. And we say that if you have a metallic surface, there'll be charges built up like this, and the electric field will look something like this. Agree? That is the E field. You can clearly see that the normal component of the electric field is not 0 on a metallic surface. But what component is 0 on a metallic surface? Anybody? What component of the electric field is 0 on a PEC surface?
The tangential
Very
component.
good. Okay. Tangential, and the way to say it usually is that n cross E equal to 0 on a metal surface. Because when you cross anything with n is a unit vector that is normal to the surface, it will automatically pick up the tangential component of E. Only the tangential component of E when crossed with n give you non-zero values. And if you set this to 0, it gives you tangential component of E equal to 0. But what you say was actually confusion with the B field. A B field will look like this. Okay, the B field will look like this. And that the boundary condition we have for a metal surface is that the normal component of the B field is equal to 0 because there are no magnetic charges. Since there are no magnetic charges, the normal component has to be 0. What about the tangential component of B field? Should it be 0? Anybody? The tangential component of the B field is not 0. And what is the physical reason for that? Anybody?
Surface current.
That's right. You have to have surface currents. Remember, we studied the case of a perfect electric conductor and a superconductor. When you put a magnetic field close to a superconducting surface, there has to be eddy currents flowing on the surface to push out the magnetic field. Those eddy currents become surface currents when you have a superconductor or a perfect conductor. So we're not going to worry about the B field boundary condition here. Only one of the two boundary conditions is necessary because we look for the boundary condition from Faraday's law. Okay, so tangential E equal to 0 is the necessary boundary condition. And this actually follows from Faraday's law. Okay, if you study this law properly, you need that boundary condition. And only one boundary condition is needed. Okay, only one boundary condition is needed. So let's see how we can impose this boundary condition. Then you look at the E field. The E field is defined to be given by this. So we need to find the tangential component of the E field. So we need to find the fact that when would n cross curl cross z psi of h equal to 0? Okay, when would this be equal to 0? And then again, you use the famous back of the cap formula to simplify this, and you will have two terms. And it turns out that one of the two terms is 0 because it involves n dotting with z. And then this equation becomes something like n dot psi of h equal to 0. Okay, and n dot grad can also be written as n dot grad sub s, where grad sub s is something that only has x component and y component. Okay, so this is usually also written as n dot grad sub s psi sub h equal to 0. And if you can figure out what the physical meaning of that is just the normal derivative. It says that the normal derivative of psi sub h is equal to 0. And this is usually called the Neumann boundary condition. Okay, Neumann boundary condition. And you need this boundary condition in order to solve the PDE. We have arrived at the PDE. That PDE is given to be this. Okay, you have to add this boundary condition in order to solve it. Any questions regarding this? So that is for the TE case, and it will be interesting to see what the TM case looks like. So we say that we can break the problem into TE and TM case, and you can go through the same exercise. Then in the TM case, HZ equal to 0, EZ not equal to 0, and you can construct an H field to be the curl of the Z hat of psi sub ER. And by this construction, HZ is clearly equal to 0. Okay, and you also have the fact that divergence of H equal to 0, which is necessary since there are no sources inside the waveguide. And you can go through the same argument as we said before and argue that Laplacian plus the beta square of psi sub E must be equal to 0. Okay. Again, you have a metallic surface, and you would have the same boundary condition as the TE case, which is the n cross E equal to 0. And this makes things a little bit more complicated. Okay, this makes things a little bit more complicated because it's not easy to find the E field. So in order to find the E field, you know that the E field is proportional to the curl of H from Maxwell's equation. Okay, you can just take the curl of H, that gives you the E field. And then if you look at the E field, then it's proportional to curl of Z psi E. Okay, let me put the parenthesis around here. And again, you can use the back of the cap formula and show that this can be written as the gradient of the divergence of Z psi E. Okay, and then this becomes that. But then what you should have is that, let me see. You should have two terms, I'm sorry. When you use the back of the cap formula, you should have two terms. You have one term that looks like this, and then you have another term that is like the Laplacian. Okay, and because you are looking for a waveguide solution in the source-free region, the Laplacian of psi sub E is just equal to minus beta squared times psi sub E, and this whole thing can be now written as, and this is just partial Z psi sub E plus beta square Z psi sub E. Okay, and we want tangential E to be 0. We want tangential E to be 0, which is that we want this to be true. And this is definitely a tangential E component on the waveguide wall because it is something that is pointing in the Z hat direction. And if you were to let psi sub E equal to 0 on waveguide wall, this term is definitely 0 on waveguide wall, and then you will have this satisfied. But what about the first term? The first term, if psi sub E equal to 0 on the waveguide wall, then partial Z psi sub E is also 0 on the waveguide wall. Okay, and then if you take the Laplacian of this 0, then the electric field is also 0 on the waveguide. Well, you can convince yourself of that. If you were to take the gradient, which is producing the tangential component of E, it would be 0. Okay, so if psi sub z is equal to, on the waveguide wall, this is equal to 0, and you can also show that n cross del partial z psi sub E equal to 0. Okay, which means that when you want to solve this PDE, the boundary condition is this. This boundary condition is called the Dirichlet boundary condition. Okay, and then so you have two cases that we have considered. One is the TE case, where we have it reduced to this simple problem, which is a wave equation with a Neumann boundary condition on the waveguide wall. Okay, the boundary condition that we have arrived at is the Neumann boundary condition that we have found here. But for the other polarization, we also have the same equation to solve, but with a different boundary condition called the Dirichlet boundary condition. Okay, so the solving for the solution of a mode or a waveguide reduces to solving a PDE, a mathematical problem, where you solve for the solution of this PDE. PDE stands for partial differential equation with the correct boundary condition. You can further assume that all the solutions of interest to us are solutions of this kind. Okay, that we are only interested in phi of r that is a waveguide mode propagating in the z direction plus or multiplied by something that varies in the transverse direction. R sub s here is x plus y. So this means that this function is a function of x and y only. So if we are looking for solutions of this type, which corresponds to traveling waves in the positive and the negative direction, and you can say that in that case, then the Laplacian can be written as a transverse Laplacian plus partial square partial z square. Okay, partial square partial z square. Transverse Laplacian is just the same as, let me write down what the transverse Laplacian is for you. It would be this one plus this one. Okay, and if you have this operator expressed in this manner, operating on a solution or wave function that has this kind of dependence, okay, what do you think would happen to partial square partial z square? What would happen to partial square partial z square if you want to seek a simplification to this Helmholtz wave equation or Helmholtz equation? What will happen to partial square partial z square? Anybody?
Minus beta square and beta z square.
Very good. Okay, because of this dependence that we have assumed, then partial square partial z square becomes minus beta z square. Okay, so I can write my Helmholtz equation like the first one into something like this plus beta square psi sub e, or it can be psi sub h as well. So just let's assume that it evolves into something like this, and then I can call this beta s square. So the equation that I have becomes a 2D equation, and it involves only the transverse Laplacian, and this can be written as the function of only x and y, because I can let my 3D function to be something like this. Okay, so this equation is a simplified equation. It's called the reduced wave equation. And it is the equation that we need to solve. Okay, so let's take a very simple example using the remaining time that we have, which is that of a rectangular waveguide. In the past, we have only been doing theory. And let's take this as an example. Let me see if I can get rid of this. Okay, you get rid of that. And then we can take the key TE case first for the rectangular waveguide. And of course, this one EZ equal to 0, HZ is not equal to 0. Sorry, it should be the other way around for the TE case. And then the boundary condition that my size of H. So for TE case, I look at size of H, and it should be expressible in terms of size of HS, XY, with a dependence of a propagating wave. Okay, and if that is the case, then the reduced wave equation that this satisfies is equal to that. Okay, is equal to that size of HS, x of y equal to 0, with the boundary condition that on the waveguide wall, okay, this boundary condition should be satisfied. Well, you can write the solution for this equation quite readily because the transverse Laplacian would be just equal to that. Okay, and you can use the separation of variables and show that psi HS XY has to be something like A cosine of beta XX cosine of beta YY. Okay, you can also choose sine as well, but we have chosen the cosine so that on the waveguide wall, at least on the one of the two walls, like the x equal to 0 wall, which is this wall over here, and the y equal to 0 wall is this wall over here, and this would satisfy the Neumann boundary condition on the two walls. And then in addition to satisfying the Neumann boundary condition on this wall and that wall, you will have to take its normal derivative, and that you know how to do, which means that if you're on this wall, what is the normal derivative? What direction should you differentiate this function to find the normal derivative of the scalar potential or the pilot potential on the waveguide wall? Anybody on this wall, what is the normal derivative? And what derivative should I use to get the normal derivative on this waveguide wall? Or also on this waveguide wall, the two walls are parallel to each other. The two normals are also the same. So the normal derivative on this waveguide wall is the same as the normal derivative on that wall. And what should I do in order to get the normal derivative? Anybody? What about Zheng Liu? What do you think that normal derivative should be?
So I was not quite catching.
Okay.
Can you repeat the problem?
Yeah, I want to ask you, you have to impose this normal Neumann boundary condition on the waveguide wall. So the normal derivative from this wall and that wall would be differentiating in the normal directions, and that would be differentiating with respect to x. And then you have to impose the fact that the normal derivatives have to be equal to 0 on the top and the bottom wall, and then those two walls you have to differentiate with respect to y. Okay, you differentiate with respect to x, this becomes a sine. You differentiate with respect to y, this becomes a sine. You impose the boundary condition to be 0, then you will find that, in fact, beta x has to be n pi over a, and then beta y has to be n pi over b. Okay, and those are the beta x and beta y that you have found. But then the dispersion relationship has to be satisfied inside the waveguide wall, because these are solutions to the Helmholtz wave equation. Okay, beta z squared must be equal to beta s squared, which is omega squared mu epsilon. Okay, you can show that this to be true, and hence beta z has to be equal to omega squared mu epsilon minus beta x squared minus beta y squared. And if you plug in the value of beta x, this would be n pi over a squared minus n pi over b squared. Okay, you'll find that if the frequency is too low, and if you pick a certain m's, okay, this number becomes imaginary. When this number becomes imaginary, it says that you do not have a propagating mode anymore in the z direction. Okay, and you will have evanescence wave. If omega squared is less than a certain frequency, and that frequency is determined by the second term called the cutoff frequency, and it depends on m and n. Okay, so each of the mode, if you choose a certain m's and if you choose a certain n's, then you're actually picking a special mode of the waveguide. And that particular mode has a cutoff frequency when omega is less than that value over there. Okay, so you can go and read the lecture notes for TE mode. 2E10 mode has lowest cutoff, and it's the mode that is most important. It's usually called the dominant mode. Okay, this is called the dominant mode. Okay, I'll stop here since I'm running out of time. Are there any questions that you may have for this lecture before we depart? Anybody? Okay, no questions. Very good. So you have to turn in your homework today, and I'll give you a new homework to work with. Okay, and please read the lecture notes. And I believe that many of you have had these materials in your undergraduate courses, and then you can just read this as a review. If not, you have to read it seriously in order to understand these materials. And we are ready to help you whenever you have a question on these materials. Okay, I'll let you go and take good care of yourself and keep safe out there, since it's still not very safe.